Good afternoon, everybody. My name is Drew Ellsbury with Heat Pipe Technology, and I'd like to welcome everyone for joining us for this webinar today. Before I get started, got a chat window put up here. Just want to make sure everybody can hear me okay. So if you can chime in and just say yes, no, speak up, you're great, something along those lines, I would certainly appreciate it. All right, good stuff, good stuff. All right, so I'm going to hold off questions till the end. I'm going to answer any questions at the end, but if you have some questions throughout that you want to go ahead and jot down on the chat window so you don't forget, please feel free to do so. If I don't stop and answer them at that time, if it's not pertinent to what I'm talking about or I'm just on a roll, I will definitely catch up with it at the end. With that said, let's get started. So people might have joined in last month when we did a webinar for all kinds of heat pipes, heat recovery, and dehumidification. We found that one was going a little bit long, so we cut this in half. We're going to do just HRMs, or heat recovery heat pipes, this time around. And then next month, and I'll remind you this later, next month we're going to focus specifically on the wraparound heat pipe. So what I'm going to talk about today is the heat recovery heat pipe. I always like to start off with a quick refresher on what a heat pipe is and how it works, or more specifically how our heat pipe works, because the HPT heat pipe is a little bit different from the others that are out there. But the main focus of today's webinar is on the various applications in which the heat recovery modules can be used, from the various configurations that we can work with, as well as specific applications like high temperatures, data centers, using heat recovery heat pipes in kitchen hood ventilation, which will actually meet an ASHRAE standard. And then what's interesting, if you're familiar with the wraparound heat pipe and that it's used for dehumidification, there's the heat recovery heat pipe for dehumidification. So gonna cover that as well. So I'm sure everybody here is an expert when it comes to heat pipes, but that's not going to stop me from showing this picture and telling you how a heat pipe works. So when you strip away the curtain and the black magic that surrounds the heat pipe, then it's really a tube. It's got refrigerant in it, and when you apply heat to one side, that refrigerant is going to pick up the heat. It's going to boil, and when it boils, that creates a pressure differential, and that vapor is going to flash to the other end of the heat pipe, where it's now in contact with a cooler air stream, gives off that heat, condenses back to a liquid, and then that liquid goes back to the other side where it's that space left by the vapor, and that cycle is just going to repeat. So it's going to pick up heat on one side and dump it to the other side. We don't need a pump or any power to make it work. All we need is that delta T. It's going to create a delta P, and you're going to get heat recovery, heat transfer from one side to the other. Now the heat pipe you're looking at right there is the traditional heat pipe, what we call the single tube type heat pipe, because it's all happening within one tube. And you'll find that some of the heat pipes out there use this single tube approach, and because the liquids go in one larger tubes to make that happen. So when you see heat pipes using 1-inch aluminum tubes, that's why they're so big. It's because you got the liquid going this way and the vapor going that way, all inside the same tube. We do it a little bit differently. We use what we call a loop circuit, where instead of a single tube with the heat going back and forth, we actually have what kind of looks like a racetrack, where you're going to have the liquid going one way, and let's say we're going from left to right here. The liquid's going to enter that hot air stream. It's going to pick up that heat and boil. It's actually going to go up the loop and then loop to the other side, where then it contacts the cooler air stream, gives off the heat, condenses back to a liquid, goes down the loop, and it just keeps going in a racetrack type circuit. And then when the season changes and now that hot air stream is a cold air stream, that refrigerant just changes direction. So the fact that we got the liquid and the vapor all traveling kind of in unison, it allows us to use smaller half-inch copper tubes. And that's made us very advantageous, especially when it comes to performance Smaller tubes with the same amount of rows allows us to add less static pressure to the system. We get a little bit more heat transfer out of it, and you'll find that some other heat pipes need what they call a tilt mechanism when the season changes to make sure that liquid's always running downhill. We don't need that. We just, because of this loop circuit, the refrigerant's just going to change directions all by itself. So instead of a bunch of single tubes stacked so many high, so many rows deep, so long, we have a bunch of individual loop circuits stacked so many high, so many rows deep, and so long. And each of these circuits are individual, so if, really bad things happen and one of those circuits got punctured or something like that, you're just going to lose the charge of one loop. You're not going to lose the charge of the whole system. So just a very small amount of the capacity is lost if something like that were to happen. But they all act together as one complete. So for heat recovery, our heat recovery module is aptly named the HRM. And it's basically used to take heat from one side to move it to the other side. So in the summertime, we're going to take that hot outside air and we're going to pre-cool it by dumping that heat into the cool. We are a sensible only heat recovery device, which means that we only work with delta T's. So we're going to be at 6 rows, about 55% effective, which means that whatever that total delta T is, or from here, if it's 75 exhaust, 95 outside, that's a 20-degree delta T, we're going to recover about 55% of that temperature. So we're going to pre-cool that 95-degree air by about 11 degrees and cool it down to 84 degrees so the cooling coil doesn't have to work as hard. And then conversely, when it's cold outside, now we're going to take the heat from the exhaust air and actually put it in the outside air stream to preheat that air so the boiler or whatever's being used for heating doesn't have to work as hard. And still going to be the same effectiveness, about 55%. So pros and cons. Believe it or not, there are some cons to the heat pipe. Yes, believe it, unfortunately, but they're very few. The biggest con is that we are a sensible only device. There are devices out there like wheels, fixed plates that recover latent heat, so when it comes to total enthalpy, they're going to than us, especially in the summertime where there is latent heat. When it's cold outside, we're still slightly less effective than the other devices, but now we're all sensible only anyway at that time, so we're not that much at a disadvantage. But in the summertime, you'll find that we are quite a bit less effective enthalpy-wise because we're not recovering latent heat when other devices are. And we do have some installation limitations, basically because whenever the airstream, we have to have the airstreams level to work year-round. If we had any kind of slope to the heat pipe, that liquid's only going to go down, which means we're only going to work when the warmer airstream is at the bottom. And there are some applications where that's perfectly fine, and we take advantage of that. But that is one of the limitations that we do have. Plenty of pros, though. The fact that we only need a delta T to operate means we don't need any power, we don't have any moving parts, and again, like I said earlier, we don't need a tilt mechanism. So from a maintenance standpoint, there's hardly any maintenance involved with a heat pipe. We get a lot of jobs because we're very maintenance friendly, and the owner just wants something that they can kind of set it and forget it. The maintenance for a heat pipe is clean it. We recommend clean it whenever you clean the coils, and you'll be good to go. That's really all that's involved. Another big advantage to the heat pipe is that we don't have any cross-contamination. We're not going to carry any air from one airstream to the next. So when you're comparing us to, let's say, an energy wheel that does have more effectiveness than we do, if it's a scenario where cross-contamination is a concern, it's not even an option where we would be. So the kind of jobs we see where cross-contamination is a concern, laboratories, hospitals, pharmaceuticals, paint booths, We've seen a lot of bus garages lately, and even nail salons. I mean, any job where you don't want something that's being exhausted to get back into the outside air. You can use a heat pipe, and actually you'll find that we'll put a partition between those two air streams to isolate them, but we even go a step further at HPT and fill it up with a foam. And this is very similar to the foam that's used as insulation for inside of air handler cabinets. We are not insulating anything, but what you do when you pour this foam into that partition, it spreads out and hardens, and it's going to, our tubes are going in between those end sheets right there, and even though we expand them, there's still some tiny holes around and cracks that might still be there when you put a microscope to it. So we just want to make sure that we fill in all those holes, and that's what that foam does for us. So we're obviously an extremely durable device. I mean, we're made out of copper and aluminum and steel. So we're going to last a long time. I mean, probably up to 20, 30 years, depending on the environment. And we're nice and compact, too. So, we can take up the space that a wheel does, depth-wise, but actually fill up the whole air tunnel and not leave the corners to be unused. And we're nice and flexible. I mean, you can actually design the air tunnel or the air handler, design us around the air tunnel versus having, where if you got a wheel or a fixed plate where you got some set sizes, you have to size your air handler and accommodate for those devices. For us, we can make them longer, we can make them taller, we can really fit your needs by just adjusting our dimensions. And we can handle some higher exhaust air temperatures as well, and we'll touch on that because most devices can only go up to maybe the low hundreds to maybe 150 degrees. So if you've got some industrial type applications out there or process applications where you've got some higher than usual exhaust air, we can actually go up to 200 degrees and recover that heat. Above that, and our refrigerant, it's just above the hump on the pH curve, if you remember those days, and basically above that hump, the refrigerant's just not anything for us because we're phase change. And we also have a superior RER. So I'm sure some of you are going, oh yeah, of course, RER is awesome, and heat pipes are wonderful for RER. Some of you might, on the other hand, think, what is RER? Well, let's answer that because that's an excellent question. RER is the recovery efficiency ratio, and it's actually defined by guideline V out of AHRI as the BTUs per watt hour, or how many BTUs are you recovering versus how much watts are you adding to the system to go get those BTUs. So if effectiveness is like capacity for a cooling equipment, then RER per ton. It's not just looking at how much BTUs are you getting, but how much energy are you using to go get those BTUs. So for us, all we're doing is adding a little static pressure to the system. Again, we don't need any power to operate, so we just add a little bit of static pressure, which means there's a little bit more fan power involved to go get our BTUs. You compare us to something like a wheel that's adding more static than we are, so even more fan power, but also has a motor to turn the wheel. You also have to account for leaks and purge and stuff like that. There's a lot more power being added to the system to go get those BTUs. So I'm just going to run a quick example. I picked St. Louis because it's kind of average when it comes to the USA environment, kind of right in the middle of the country there. If we looked at just total energy for St. Louis, Missouri over a given year, you'd find that we're recovering less BTUs in the summertime. Well, actually all the time, but in the summertime you'll see that, or in the cooling season, the wheel is able to recover quite a bit more BTUs than we are, simply because that wheel is recovering latent heat and we're not. But you look in the heating season, again, there's now we're both sensible devices. So we're still a little bit behind, but it's a lot closer. So if you looked at the whole year and put all those BTUs together, we're naturally going to recover less BTUs than a wheel does. But if you're looking at the power being added into the system and take into account that that wheel is adding maybe twice as much static than we are, but also has a motor to keep it turning, also you have to add more air to it to overcome leaks and purge and stuff like that, you actually find that a wheel may require twice as much power to operate. So if the RER is the BTUs per hour divided by the watts, or basically the first slide divided by the second slide, you'll find that in the cooling season, we're still behind because we were not recovering latent heat. So anytime that we're not recovering latent heat and a wheel is, we're not only going to be further back from a BTU standpoint, but we're going to be further back from an efficiency standpoint. But when you look at the heating season, where there's a lot more there's a lot more delta T's to go get anyway, but we're not hurt by the fact we're not recovering latent heat, you actually find that we're a more efficient recovery device because we're just adding static pressure and not as much as a wheel. So even when you add up the whole year for a place like St. Louis, you find that we're still, over the whole year, the more efficient energy recovery device. So you'll find this is in St. Louis, you'll find as you work your way north and it starts getting colder and there's less cooling season to hurt us and more heating season to help us, we're going to be even more efficient. Conversely, you start working your way south where it's more humid and more cooling season, we become a little bit less efficient. So if you have any applications in specific locations you want us to take a look at to help you with some full comparisons, because that's what the RER does. It allows you to, effectiveness is I'm not saying effectiveness is not important. It's extremely important to know how much load is being shaven. But if you're looking at true energy, and you should be if you're using an energy recovery device, you should step back and look at the big picture, and the RER is just a metric that helps you do just that. So if you want us to look at some specific comparisons or locations, not only are we happy to help you do that, but you can actually use our software to calculate RER by running a bin analysis as well. So another cool thing we can do is actually split apart the air streams. We call it our split passive heat recovery module, or the HRM-V. That V is there because when we split them apart, we pull the circuits together in common headers. So you'll see that on the top there, that's the vapor header going from one side to the other, and on the bottom is the liquid line. Every two pair of headers. When we have these headers, now the circuits are within tubes that are running vertically within the heat pipes to go from header to header, and it's those vertical tubes that give the HRM-V its model name. The V is for the vertical tubes. Now we do have some limitations. Again, we still don't need pumps, but with that means we can only run so far before the refrigerant's just going to stop moving. The head is only going to push it so far. So we can actually run up to about 40 equivalent feet, and that equivalent feet isn't just distance from one airstream to the other. That's the actual piping run and resistance that the refrigerant's traveling. So when we have, when we add some elbows in there, that's going to add some resistance. And if you have to zigzag across the floor, it's the actual run that refrigerant is making. So whether we had a zigzag across the floor or even go from one parallel airstream to the next, it's all the same to the heat pipe as long as it's within 40 equivalent feet. You also notice there that there's some valves on the liquid line. Those are modulating valves. We actually use those. We can start modulating the refrigerant flow for temperature control. So if we're capturing too much heat, say we're in economizer mode, or even for frost control, you want to start limiting how much heat recovery you're getting. We can start modulating the flow to control that temperature. Another cool thing this allows us to do is take a parallel flow situation and make it counterflow. So if we had the side-by-side HRM and had to be parallel airflow, we're going to lose some performance. Instead of 55% effectiveness, we're probably going to be closer to about 40% effectiveness, give or take. But if we split them apart, we can actually cross the lines so that counterflow, so you don't take that performance hit. With that said, it's worth noting that the HRM-V, because we're pulling those circuits to common headers and making them run a further distance, we we do lose a little bit of performance, we're no longer at 55%. We're going to be closer to about that 40% effectiveness range as well. We can also work with an elevation change. We can actually get up to about 50 feet in elevation. And when we have elevation, that means we've got some gravity helping keep the refrigerant moving. So we can actually run a little bit further. So if we get up to 50 feet of elevation, that means we can get about 100 feet of an equivalent run in, which is nice. The only downside to this is that we're only going to work in one season now, because that liquid is only going to go down. So you want that warmer airstream at the bottom to take that liquid and boil it so that vapor goes up, and then when it condenses after giving off that heat, that liquid can only go downhill. So typically, the majority of the time you're going to want heating season recovery, so you'll want that exhaust airstream to be at the bottom to get your best bang for the buck. And you can see that, typically we've got the air handlers or the ducts on different floors, and, it doesn't really matter. If you have 50 feet or even 10 feet, you don't have to have a longer run. It just allows you to have that longer horizontal run. So another cool thing we can do is do what we call our over-under heat recovery module, or the HRM-O. In this case, we just take the HRM and flip it up 90 degrees. The obvious downside there is now we're only going to get heat recovery when the warmer airstream is at the bottom, but there are plenty of applications where that's all that matters anyway. One such application would be with pool units. In pool units, you're not really wanting to cool the pool area. You're going to want to heat it up. So in that case, make sure that the outside air, that cold outside air, is coming in up top, and the warm exhaust air is coming in at the bottom. That's all you care about anyway. It's also beneficial that we are a sensible only device. When it comes to pool areas, you actually want to get rid of that humidity instead of bringing that latent heat back in. So the fact that we're only recovering sensible heat is a good thing when it comes to pool units. And it's also good that we don't have cross-contamination, because any of those chemicals, you don't want to bring them back in. We're going to exhaust all of them right out of the room. So if you have any if you have any pool units or applications, the heat pipe's going to allow you to shrink that system down, save some energy, and it kind of fits right in line with what pool units want to do. So again, I mentioned that we can handle higher exhaust air temperatures. I wanted to run a quick example. We can actually go up to 200 degrees. That's as high as our refrigerant allows us to go. Our standard refrigerant, by the way, is R410A. We will go to 134A when we do our split passive, but we'll also go to it when that exhaust air temp is above 150 degrees, just because the peak of the pH curve is higher for 134A than it is for 410, so we can handle a higher temperature. In this case, I'm just going to look at where exhaust air is 120 degrees. So if it's 0 degrees outside, we're going to recover about 55% of those delta T's, so we would heat that outside air up to about 66 degrees or so. So let's say that 66 degrees is perfectly fine for heating that space. But that's, of course, with 0 degree air. Let's now say that it starts warming up outside, so you got 40 degree air. Well, now instead of 120 degree delta T, we're looking at an 80 degree delta T. We're still recovering about 55% of that, so now instead of heating that up to 66 degrees, we're going to heat it up to 84 degrees. Well, the problem with that is that might be too hot for the space. So what you do to control the temperature on a side-by-side is just add some bypass dampers. Bypass dampers are you can actually select them in our Select Plus software. We will provide them here. We don't have to if it's going in an air handler and the air handler manufacturer wants to provide their own dampers. That's certainly fine with us. We don't make dampers, so it doesn't hurt our feelings, but we do give you that option. The bypass damper is simply for temperature control. If you're looking for full economizer control and want to reduce the static when you're not using the heat pipe, you would want to use some face dampers, and in that case, we do not offer face dampers. That would be something that would need to be provided by the third party. So run a quick scenario. Again, you go and select our Select Plus software. You can run some bin analysis at all kinds of conditions. This is one I did for Albany, New York. Just considering a 25,000 system, CFM system, running 24/7 all year round. They're always exhausting 150-degree air, and they want to supply 55-degree air all the time. And for the bin analysis, I was told to use 75 cents a therm. So if we take a look at that, and again, this is right out of Select Plus, and you run these scenarios, and let's say it's 0 degrees outside, 150-degree air, we're actually going to be about 60% effective at this condition, which means we're going to heat up that air by 60% of that 150-degree delta T, or 90 degrees. Of course, if they want 55-degree air, 90 degrees is going to be way too hot. So what do? You put a bypass damper on it. Now you'll find that within Select Plus, on the exhaust side, we're still showing that 514-minute face velocity because we still have all the air going through the exhaust side, but now we're bypassing around the supply side. So you can actually see that the resulting air that's going through the heat pipe that's not being bypassed has a lower face velocity and therefore a lower pressure drop as well. So those numbers are showing you what's actually going through the heat pipe to hit that temperature, and you can plug that in as well, like to say what temperature to go to and control to that certain set point. And you can even go a step further, run a bin analysis, pick your location. In this case, it's Albany, New York. And again, we're assuming that we don't want to get any more than 55-degree air coming out of the heat pipe. So you can see on the supply air leaving, they're all capped at 55 degrees. So anytime the air is warmer than 55 degrees, we're not doing anything. It's full bypass. And anytime it's lower than 55 degrees, we're only passing enough air through the heat pipe to get 55 degrees. So assuming that that's our cap, you'll see that for those bins where it's cooler than 55 degrees, we're going to save, at 75 cents a therm, even taking that static pressure hit of $2,500 you see below, we're going to save just under $26,000 a year. That's going to give you, depending on how much the install is, somewhere, probably between a 3 and 5 year payback for that setup. Now that's if we capped it at 55 degrees. Let's say it's not comfort heating. Let's say it's process heat, and therefore even on a hot day of 95 degrees, we still want to take that heat and heat it up. That's going to be still exhausted at 150 degrees. Well, now we're taking every bin of the year and taking as much heat as we can all the time, not bypassing anything. Now instead of $26,000 in savings, you got over $300,000 in savings. Now we're not talking years of payback. We're talking days or weeks. So if you have any process type applications, the heat pipe makes perfect sense because not only are we going to give you year-round recovery and year-round savings, but we're going to do so at higher exhaust temperatures than other devices are going to allow you to do. And I did say that our max temperature is 200 degrees. If you have process heat that's above 200 degrees, that's fine. You can always dilute the air with some of the outside air to bring it down to 200 degrees to capture that heat. There are other systems out there, other heat pipes actually, that can handle higher temperatures, but they certainly cost more. So if it costs less to dilute the air in some way to use our heat pipe versus a more expensive type heat pipe, it's probably in your best interest to do so, and we'll happily discuss that with you and see that it is. So another cool application is data centers. Of course, data centers, you got your stacks giving off all kinds of heat, and there's plenty of data centers out there. We got these mystery things called clouds, and I'm pretty sure they tie into all these data centers that are out there. Of course, all these, the stacks are giving off plenty of heat, so you got what these call these CRAC units, or computer room AC units. They're typically feeding cool air under the floor, and then that cool air is going to cool all those stacks. It's giving off all that heat. Heat's naturally going to rise So we're going to cool those stacks, heat's going to rise, and then of course all that hot return air goes right back to the CRAC unit, gets cooled, and the whole system repeats. So how do you optimize this system? Well, the way they're currently doing it is simply encasing those stacks to reduce the amount of airflow that's needed, and then actually ducting that return. That's one way to optimize the system. Of course, another way is to use some heat recovery to reduce the amount of load on those CRAC units. And of course, a great way to do that is with, you guessed it, a heat pipe. So let's say the data room is set for 75 degrees. I believe that's what ASHRAE recommends. So anytime that it's cooler than 75 degrees outside, we could essentially use the heat pipe as a heat sink to whisk that heat away to the cooler outside air environment to cool that air before it goes back into the CRAC unit. One of the benefits of the heat pipe versus other devices that can do this is that, again, we don't have any cross-contamination. Now, we're not talking harmful contaminants that are going to hurt people. We're talking harmful contaminants like pollution that's going to hurt servers and stuff like that. So there actually is a benefit to not bring in some of the outside contaminants that are, smoke or fog, or not fog, but just stuff that's coming off cars and all that stuff. You don't want to bring that into a data room. So the heat pipe helps in that respect. We also, again, don't need any power. The only power you're adding is this fan. You got to have some kind of fan blowing air across the heat pipe, but you'd have to have that on any device that you use. So for the heat pipe, we don't need a motor or a pump or anything to work. So we're passively cooling it, which means that it's about as minimum maintenance as you get while getting heat recovery in a data center. And that's obviously a benefit for all these data centers out there. The less they have to go out there and maintain them, the better. And you can actually go one step further if you're in a drier environment especially. You can actually use an evaporative cooling to spray some water on the outside portion of the heat pipe, and it fools the heat pipe, so to speak, to see cooler air conditions. So now instead of a 20-degree delta T, it might see a 30-degree delta T. And if that's the case, you're going to get about 50% more heat removed. So this is certainly location dependent. It's also something you can plug into Select Plus, our software, and once you pick your location, it'll show you how cool you can actually get the air based on the wet bulb at those bins. So by being able, especially to put an evaporative cooler on there and get even more BTUs, and do so by simply adding a little bit of static without any power, now we're not only a very effective device, but a very efficient device, especially when it comes to RER, which is always great. And you can actually use our HRMO, the over-under, because again, with a data center, you're only concerned about pre-cooling that air and whisking away that heat. So if you wanted to put that, the fan unit or the outside portion on the roof, that's perfectly fine because all you're doing is pre-cooling anyway. So whether you're putting it on the sidewall or on the roof, it's gonna do the same thing for you. So ASHRAE standard 90.1. One of the things it gets into is kitchen exhaust systems. And actually, if the total airflow rate that's being exhausted out of kitchen exceeds 5,000 CFM, ASHRAE 90.1 requires that you do one of three things. One is that at least half of that replacement air is transferred air that would be otherwise exhausted, so that's an option you can do. You can do a demand ventilation type system, a little beefier control setup, or you could use a heat recovery device that ASHRAE says has to be a sensible device, and per the IMC, it has to be a coil type device because they recognize that air is going to be grease laden, and it's a lot different getting that out of other devices than it is something like a heat pipe where it's a lot easier to clean. So, and the minimal effectiveness is 40%, which is a piece of cake for a heat pipe. So if you have any kitchen exhaust systems and they have to meet code, use that heat pipe. Yeah, they've got to do a little bit more cleaning than usual, but it's going to save them some energy and help them meet code. And lastly, another cool thing you can do if you're familiar with the wraparound heat pipe, its sole purpose is for dehumidification, but that's for next month. But the HRM can be used for dehumidification as well. In this case, we're actually, wrapping around the air, so to speak. So we see this a lot on rooftop units where you've got the return air and the supply air vertically alongside each other. You could actually just run those ducts together and lay the HRM flat, and now we're going to pre-cool the incoming return air and then take that heat and use it as reheat to control humidity. So whether we do that on this type of setup, you could also have, if you had for just a vertical air handler in the duct running horizontally in a space, we can do the same thing in horizontal duct and set up the natural side-by-side type arrangement. But I wanted to show this because it's a little bit different, and there's more considerations involved. So one, obviously you got to filter that air on both sides. The air is naturally going to be filtered on the supply side, but you're going to want to filter it upstream of the return side as well. But more importantly, in this type of setup, you're gonna have a chance for some condensation, depending on where you are. And if it's in a horizontal duct or in your air handler, it's a piece of cake. You have a drain pan. But if you've got vertical duct, it's a little bit more involved, but you still need to be able to drain that condensate away. So make sure if you had this type of setup that you account for some means of draining that condensation at the bottom of that vertical duct. And a lot of times we see a custom curb adapter being made. You just boost it up a little bit and actually have a curb adapter with the heat pipe inside where you're bringing those out, the supply and the return duct together. I did want to point out one specific type application that we've seen a lot of. This is actually something that our rep in Colorado has been very successful with. So nail salons, they have a new code out in IMC that requires all new nail salons or in your remodels to be 100% outside air, because they recognize there's a lot of nasty fumes in nail salons that need to be fully exhausted. So the new IMC, if anybody has a remodeling, whether it's HVAC related or not, that code inspector might come in and tell them that, well, hey, since you're remodeling, you've got to put this up to code and make this 100% outside air. Well, one thing they can do is rip out the whole system and put in a nice new 100% outside air system. But my guess is they probably don't want to spend that money. So putting a heat pipe or the heat recovery heat pipe is a nice, less expensive way to meet code. Because it's going to reduce the load on that existing system, so that that existing system can handle the higher outside, the higher load that's coming in. And because we don't have any cross-contamination, we're not worried about reintroducing those nasty fumes back into the airstream. So if you have any of these nail salon engineers out there, this is something to keep in mind that could save those owners a lot of money versus replacing their entire system. And last but not least, just a shout out to our Select Plus software. If you haven't seen it yet, what are you waiting for? It's very easy to use. You don't have to download anything. You just go to heatpipe.com. You request a username, you create a password, and then it's all there for you. Nobody has access to what you're working on unless you invite us to take a look at it. You can do everything from performance selections to getting drawings to site charts to bin analysis, and it's very easy to share but with us, with your teammates, with your customers. And if you need any help, please give us a call. We'd love to walk you through it. It's a really nice system, and So with that said, I wanted to open it up for any questions. Let's see, where's that? There we go. Did I have any questions during the presentation? Got some speaker talk. Okay. Well, Mazen, though he's so you wouldn't have heard his voice, which is pretty amazing because he loves to talk. Say hi, Maz.
Hi, everybody.
Besides that, does anybody have any technical questions that they want to send to me personally, maybe? Actually, here's a good one. Do the HRMs require drain pans? Obviously, our wraparound heat pipe that's there to remove condensation obviously needs a drain pan, but believe it or not, there's as well on either side. If it gets really cold outside, you might remove some moisture from the exhaust air, and if it's really hot and humid outside, you might remove some condensation on the outside air as well. So the answer is yes. We do recommend drain pans under the HRM, whether it's inside an air handler or inside a duct. And even if there weren't condensation, you're going to want to clean that heat pipe at some point, and you'd want some means to get rid of that cleaning agent, and that drain pan allows you to do so. Another question regarding ARI certification. No, we are obviously not ARI certified. There are actually two types of ARI certification. There's the actual getting the product ARI certified. In that case, you got to get every single model and every single configuration tested and certified for it to be worthwhile. And that is obviously extremely expensive, and we don't see the value in that at this point. We're not, it's not hurting us not having it. But the other type is actually getting the software ARI certified. And that is something that we're looking into. Now we got Select Plus going, so know that we are doing some things on our end to optimize our performance and make sure it's as good as can be before we go in and get certification. But that is on the horizon, and we can certainly keep you updated on that. That we have recorded this presentation, so if anybody did have difficulty hearing it or you want to share it with anybody, it will be available, and we'll send an email out later to everybody who attended, and you can go in and get a recording of this. Please do not pirate it and try to sell it on eBay, though I will be extremely flattered. Az will get upset, and then I'll have to get upset, and bad things will happen. But it's certainly there for you to listen to. Okay, and last question is actually a fun one. What makes HPT better than other heat pipes? Awesome question. I'm going to thank the sender of that. But, I mean, a lot of reasons. I mean, we talked about, you know, the fact that we use the loop circuit versus the single tube. That allows us to have better performance than everybody and not require a tilt mechanism, which is very helpful, especially since we want to remain a truly passive device with minimal maintenance. And achieve no cross-contamination, and if you're moving around all throughout the year, that makes that a little, you know, more risk. It has more risk to it. We also have some, you know, the fact that we can split our heat pipes apart for a split passive and add control valves and do stuff like that, it certainly sets us apart as well. On top of that, our experience and expertise. I mean, we've been doing this for 30 years ago, which we'll talk about next month. And we are a company that's owned by MyTech, which is a company that's owned by Berkshire Hathaway. So we certainly have you've got some strong financial backing, and we're certainly looking to continue our expertise and take advantage of that fact. And unlike a lot of the other heat pipes that are out there, all we do are heat pipes. A lot of the other ones, heat pipes is just one of the several. Truly are a heat pipe company. It's all we do. And we want to stay ahead of the curve on all fronts and remain that way. So I don't have any more questions, so I thank everyone for joining. And again, I'm going to be doing this again end of August, specifically for the DHP wraparound invite as well. And I thank you all. There's also going to be a survey at the end here. I'd appreciate anybody giving any feedback. Take the time to do that. We would really appreciate it. But thanks again.